All right. Molecular substances. You put the title, Molecular Substances. Yeah, we are writing a note. It's what we do in between labs and various things. Come on, folks, let's get settled. Let's get set here. Molecular substances. Molecules are a little different than ionic compounds. Ionic compounds, and I'm desperately searching in my pocket for two magnets. There we go. Ionic compounds, as I said last week, are formed when that metal atom, like sodium, gives its electron away to a nonmetal like chlorine, and they become oppositely charged. And they stick together like magnets. All right? Now, just like magnets, notice I've only got two magnets here, but if I had another magnet, what would I be able to do? Don't mind that, gravity. What would I be able to do with this third magnet? I could stick it onto the end, and if I had a whole container of magnets, which I do in there, that little Princess Fairies case there, the Disney one, don't mind that. It's full of magnets. Don't mind the case. Don't judge me. It's just a case for magnets. What could I keep doing here with these magnets? I could connect them on and on and on. And that's how an ionic compound works. If you've got a crystal of salt, like if you looked at one little crystal of salt, put it in your hand and looked at it, it would actually be made up of repeating units of sodium chloride, sodium chloride, sodium chloride. They all clump together. So ionic compounds stick together like magnets, and then they clump together to make what we see as a crystal of salt. Molecules are different. Molecules don't stick together like magnets. Molecules are actually, oops, now I'm dropping my magnets. Molecules are actually atoms bonded together and holding on to another atom. They're not stuck together like magnets, which can be pulled apart, but they're literally bonded together. So here in this picture, we've got hydrogen molecule. This is made up of two atoms of hydrogen that are bonded together, not sticking like magnets, but bonded together with what we call a chemical bond. All right? So they're different. Here I've got an oxygen gas molecule, O2, and N2 and Cl2. Here we've got some different ones. Water is a molecule. It's two hydrogen atoms bonded together with an oxygen atom. Yep?
So it's sort of like all those elements?
I don't understand. I don't know what you mean.
Like all the elements you made with the...
Yep. Yep. No, that's different. Those big, heavy elements that they made with the particle smasher, okay, what happens there is the nucleus is coming together to form a new nucleus. A water molecule, the nucleus are still separate. There's an oxygen nucleus and two hydrogen nuclei. And they're bonded together, but they're not squeezed together into one nucleus. There are three separate nuclei in that molecule. So we're not squeezing the nuclei together to make one new atom. They're just bonding together and hanging out really closely, but not turned into a single atom. Do you understand the difference? Here we're making one atom by squeezing the nuclei together. Here, there are three nuclei here. There's one right there, one right there, and one right there, and they're connected by a chemical bond that keeps them close, but not squeezed together into one nucleus. You see the difference? Okay, so that's a good thought, but it's not exactly the same. It's like these are being held together with, you could think of it like a chain, or you could think of it like a board holding these two things together. It actually isn't that. It's actually what we call a chemical bond, but it's not the same as what you mentioned there. Okay? Good question. All right. So these guys clump together, but they don't stick together like magnets. They're different than ionic compounds. Ionic compounds are together because of these attractions, and these guys are together because they're bonded together. Okay, so let's talk about what we need in order to have some molecular substances. And I'm going to bring this all up, blah, 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 blah. I hate the animations. Okay. I'd like to move that out of the way. Molecular substances, pure substances which contain two or more nonmetals joined by a chemical bond. So the difference between ionic and molecular: metal, nonmetal, opposite sides of the table, ionic compound. Two nonmetals, two guys coming from the right side, molecular substance. Okay? You might be wondering why these two nonmetals don't behave like an ion or an ionic compound. Remember, a metal wants to get rid of its electrons. There's only one of them there. So it does, it gives it up. Something like chlorine takes it. Opposite charges, they stick together like magnets. But if I were to put two chlorines together, they don't want to give up their electrons. They still want one, but they don't want to give one up. So a tug of war takes place. They start to pull on each other's electrons. But nobody wins. It's like they're the same strength. So they pull on each other's electrons, and because nobody wins, no one lets go, and so they get really close together because they're pulling on each other's electrons. They have to become good friends because they won't give up their electrons. We'll talk about that a little more in a moment. And this tug of war for each other's electrons, we call a bond. But it is different. When you get a metal in there, they don't want their electrons. Chlorine comes along, I'd like one more. Sure, take mine, I don't care. Take it away. Have it. Doesn't matter to me. So when you have a metal and a non-metal, they trade electrons, they get charges, they stick together. But when you've got two non-metals, they don't want to give up their electrons, and a tug of war takes place. So a hydrogen atom gets together with another hydrogen atom. They don't want to give up their electrons. A tug of war takes place. They form a bond. A hydrogen atom gets up close to an oxygen atom. Again, they don't want to give their electrons up. This tug of war takes place. They form chemical bonds. This big molecule here, this is a sucrose molecule, I think. It's a sugar molecule. All kinds of carbons and hydrogens and oxygens, and they're all ringed together, big, massive ring of carbons and hydrogens and oxygens, and that results in what we would call a sucrose molecule, a sugar molecule, all right? So if you have a sugar crystal, you have a pile of these big molecules all clumped together, okay? There are huge molecules. The DNA in our cell is an absolutely huge molecule. Thousands and thousands and thousands of atoms all connected together by these bonds. Even bigger than that, plastics. Plastics are made of what we call polymers, and they are huge, huge molecules made of tens of thousands of atoms to even hundreds of thousands of atoms, all linked together in one big, long molecule. So we can have tiny molecules, H2 would be the smallest, the simplest, and we can have absolutely huge molecules all linked together with these links. All right. So let's talk about a little bit about, where's my clicker here? Again, you can write the first bullet. Don't worry about writing down the second part. That's just a little bit of an information thing. So write down the first bullet. Oh, if you already wrote it down, don't worry about it. If you're ahead of the game and you wrote it down, it's not a bad thing to write. The smallest part of a molecular substance is called a molecule. So we then have what we would call a water molecule, or a sugar molecule. And these are tiny little pictures of that big molecule with all those C's and H's and O's. You can see C's and H's and O's and lots of lines representing the bonds. That's what we're going to be ending up doing at the end of today's class, is drawing these molecules. Drawing these molecules with these lines that represent the bonds. Okay, so I just wanted that first bullet written. We don't have to worry about the other one. Let me move ahead. How do nonmetal atoms bond? How do they end up forming a bond? When two nonmetal atoms bond, they share their unpaired electrons. Now, I don't know, what kind of hippie pacifist chemist came up with this idea of that they share. They're sharing. They're being so nice. They're sharing their electrons. They're not sharing. They're attempting to. They're attempting to steal the electron from the other atom, but that other atom won't let go. No, because stealing land doesn't result in a bond. So no. Do you want let me give you a silly hold on, listen up. Let me give you a silly analogy to help you think of this. Listen, please. So it's really not sharing. It's more of a mutual agreement of a tug of war. It's when two atoms get close and they pull on each other's electrons and they don't let go. Here's the silliest analogy I've ever came up with in all of my teaching career. Let's say that you're hanging out with your buddies in the hall, right? My crew down here at the end, yeah, my favorite crew. And what do? They're always pushing and shoving each other, always, forever, pushing and shoving. So let's say Josh comes up with a new way to annoy his friends. This is the way Josh is going to do it. He remembers from when he was a kid, someone said that they took his nose. I got your nose, right? I got your nose. You ever see that? Kid freaks out. So let's say Josh tries to supersize this and actually says to his buddy, I got your nose, and actually grabs one of his friend's noses. Well, pulls on it a little bit. So what does his buddy do? Well, he retaliates by grabbing Josh's nose. So what do we have here? We've got Josh trying to take the nose off of his friend because he wants that nose. And then we've got Josh's friend retaliating and trying to pull the nose off Josh's face. Well, both of these guys don't want to relinquish their nose because that would just be painful. So they have to come up with an agreement. All right, well, if you're not going to let go and I'm not going to let go, and I can't actually physically remove your nose, then we're stuck. We have a stalemate. We're pulling on each other's noses, but no one's going to let go. Now let's imagine that they take this game right to the end. I'm not letting go, you let go. I'm not letting go, you let go. Then the bell goes. And it's coincidentally, they have the same class. So how do they maneuver themselves to class? Well, they are not going to let go of their noses. So they walk down the hall, hand in nose, not letting go. What is that? Well, that's a bond. It's a really weird bond. It's a strange nose bond, but they have to move together as one because no one's going to let go. Like I said, the silliest analogy I ever thought of. But you can transfer that to electrons. A chlorine atom comes up against another chlorine atom. They both want one electron. What does the chlorine atom do? Pulls on the electron of the neighbor. The neighbor doesn't want to let go because it's not a metal. Metals let go. So chlorine isn't going to let go. It pulls on the other chlorine's atom, and it doesn't let go. So what's the only thing they can do? Is hang out together and float around in whatever physical state they're in. If they're in a gas, the chlorine gas would float around, two atoms huddled together because they won't let go of each other's noses. Just don't bother starting to pull each other's nose. That group down there, just wow. Okay, all right. So that's kind of a silly idea, but that's what a covalent bond is. So I'm not even going to bother with this. This isn't actually running. It was going to show how a sharing was going to take place, but now I'm going to draw the sharing for you. So let's write this down, and I'm going to write it on the smart board here. And no, we're not going to be drawing noses. Okay. So the example we're going to start with is two hydrogen atoms. And so let's start by drawing the Lewis diagram for the hydrogen atoms. How many dots? Now we're back to the dots, right? Remember last week we were on to the charge, and we were getting very good at looking at the charge? That's okay, that's good. But for these guys, it's all about the dots. So how many dots, and hydrogen's a special one, even though it's over here on the left, it does count as a non-metal because it's a gas. So how many dots does hydrogen get? How many dots? Yep, one dot right there. One dot, okay? And I'm going to draw a second hydrogen. Now this time I'm going to draw it as an X because I want to express its electron a little differently, okay? And what's going to happen? They're going to pull on each other's noses and they're not going to let go. Silly, silly, silly. So what do? They get close together. H with a dot, H with an X. All snug together. Now, we like to draw these a little more simply. So what we do is we switch the two electrons there for a bond. We're going to draw it like this, line H, okay? And we have a special name for this thing here. One line is called a single covalent bond, or a single bond. If I were to ask you to describe to me how to draw this, you would simply say H, single bond H. And because we're all chemists, I would know to draw a line in there. This single bond contains two electrons. So in a single bond, there are two electrons in there, just like they're pulling on each other's noses. All right? So this, by the way, right here, this particular drawing is what we call the Lewis diagram. So this picture right here, H single bond H, is the Lewis diagram. Now I'm going to be getting you to draw Lewis diagrams in a moment on your sheet, more complicated ones. And I don't expect you to draw a dot and an X and then a dot and an X, etc., 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 etc. That was hard to say with all those X's. Here's the way I want you to set it up. The way I want you to set it up, and I'm just going to draw a line underneath here. Draw your H, put the dot. Draw your other H. It's handy to put the dots facing each other. And the way I want you to think is, oh, those two are going to get together. You see how I put a line between those two? And in the end, then when you redraw it, don't draw the dots. Draw it like that, with the line. And you can think of that line as being the two electrons at the ends of the line. So we're really connecting electrons that are alone in order to draw the Lewis diagrams. Let's do some more examples, and then, like I said, I'll let you then work on the single bond practice sheet. Then we'll talk about double bonds. So let's eventually draw the Lewis diagram for two fluorines when they come together to form F2, a fluorine molecule. And we're going to draw their individual diagrams with their dots. And I'm hoping you guys are already looking at how many dots to draw. That would be awesome. How many dots does fluorine get? 7. Now, I want them to get together in the middle. So I'm going to put my 7 with my lone dot facing the other F. All right? And I'm hoping I'm insulting your intelligence at this point. What am I going to do between those 2 lone dots? That doesn't help. The opposite of what I want does not help this situation. I'm going to put a line between them. It doesn't have to be a different color, but I'm just using a different color to illustrate it. The final picture, whoops, I do want it to be yellow. The final picture, I have to keep the other dots because they're still there. So those dots have to stay, and that's the picture of F2. All right? I have no idea. Are people going ahead of me? What's happening here? That's F2 right there. Can I go ahead? I don't know how close we are following. Go ahead and do an H and an F. Some of you might be getting good enough to imagine that the H has 1 dot, that the F has 7 dots, and I need to draw that line between them. And if you can do that, that's great. That's awesome. And in a moment, I'm going to ask you to tell me what to draw. And, oh, I will go back and tell you the language. You know how to tell me how to draw a line because that's called a single bond. But if you want me to draw dots like that, these are called lone pairs. They're pairs that aren't bonded. So I would say that fluorine has 3 lone pairs and a single bond. That's how you describe that. So knowing that we call those lone pairs, someone tell me how to draw this molecule formed between an H and an F. Tell me the symbols, tell me lone pairs, tell me any bonds that need to be drawn. Yep, what do you got? H, single bond. F, 3 lone pairs on the F. That's correct. That's a good picture. Does anybody need me to go back and show you where that comes from, or did we all get that drawn? We got it drawn? Nice. Let's now do a few that involve a little more complicated scenario. So I have 1 oxygen atom, and I'm going to need 2 hydrogens in order to complete the molecule. This is going to create a water molecule. So don't be afraid. Draw the dots, and you don't have to have them lined up perfectly. Instead of a nice straight line, you could have kind of a squiggly line getting to connect the electrons. You just have to orient it correctly when you build it the second time. So oxygen, how many dots? How many dots on an oxygen? Yep, 6. So I'm going to just go 1, 2, 3, 4, 5, 6 like we normally do. Now you have to draw the 6 with the 2 separate. If you draw the 6 with it paired, you're not going to be able to connect your lines. So here's where it becomes very important that you've got the last 2 separate. So now an H over here, and I'm just going to put another H down below. Now notice I don't have things lined up nicely, but that's okay. When you're drawing your, preliminary picture, you can have this guy go to that guy, and you can have this guy go to this guy. And now when you draw your picture, you're going to just swing those H's around and draw nice little lines to represent the Lewis diagram. So by shortening these all up, I'm going to have an O. I've got my 2 lone pairs, a single bond with an H, and a single bond with an H. Okay? And that's a water molecule right there. All right? Click. So this is my last example. This is a tricky one. Give it a shot. See if you can do it. I've got 2 carbons and then 6 hydrogens. And all the connections need to be done. You might want to do this with a pencil, or if you're using your stylus, you know that you can always erase, right? So that works out quite nicely. How many dots on my carbons? 4. 1, 2, 3, 4. 1, 2, 3, 4. Notice they're all by themselves. So in the end, carbon's got to have 4 lines coming from it. I need 6 hydrogens. I don't want to put them all in a row because I'm thinking I'm going to have to put a few of them over here and a few of them over here. If I put all 4 of them on this carbon here, then that's full, and that's a different molecule. I would have created a CH4 if I fill a carbon right full of hydrogen. And that's not what I want. I need all of these atoms somehow connected into one thing. Any ideas? Yeah, what do you think? Oh, that's exciting. You want to make pairs here, here, and here? Notice I have 6 H's to deal with. Now, what you just did there, Max, you created what is called a triple bond, and we'll be doing those later. You did successfully create a molecule. Its formula would be C2H2, but that's a different molecule. That's a triple bond. That's good thinking. You can connect more than one pair, but we're not doing that yet. Yep. Okay, I'll use red again. 1 line there. Okay, then what? How many H's? 3 and 3. Yep, that's correct. H, 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 H. And again, I'm using red for no reason. And those will go with those. And C with a single bond C. And then I've got H's. Excellent. All right. At this point, I'm going to pause my movie. Quadruple bonds. Excellent question. There cannot be quadruple bonds, and I'll talk about why that is. But that's a good question. It's actually, you might think it's a silly question, but it's a good question. Well, you know, are there quadruple bonds? And there isn't, and I'll tell you why in a moment. Okay, so let's now do double covalent bonds, folks. So put that sheet aside. Put the sheet aside, and let's start taking notes again. Again, those of you, we need to get the music out of our ears, everyone. Again, this stuff is easy. Active participation will result in success, but if you're changing your music constantly or staring at the wrong sites, it will result in lack of success. All right? Stop. You need to stop talking, okay? Especially after I say things. All right. Let's talk about this situation. So we're doing the same thing as we did before. So I need dots for oxygen atoms. So let's get double covalent bond written down in our notes. Now I need dots for oxygen atoms. How many dots on an oxygen atom? Yep, 6. 6 is correct. And again, I'm gonna orient this in such a way that it's going to work out nicely. But I don't have to, but it does work good if I do it that way, because I've got the oxygens kind of facing each other. So I'm going to put those lone ones. Remember, oxygen's got to have those lone ones. And I'm going to put them facing each other. And Max stumbled upon this with the carbon atoms. In this case, we don't need 3 pairs, but we could connect 2 lines to those unpaired. So these guys could form a bond, and these guys could form a bond. Take a look at how many electrons participated in the sharing this time. How many electrons are sharing this time? 2 from each. So how many in total? 4. 4 electrons participated in sharing this time. That's what makes a double bond, that we've got 2 pairs sharing. To draw the Lewis diagram, we now just put 2 bonds in there, 2 lines. We've got to include the lone pairs that weren't participating in the bonding. And this guy, when you see 2 lines like that, we have a special name for that. That's what we call the double bond, or the double covalent bond. I'm just going to put double bond this time. And there are 4 electrons in that double bond. So if someone were to describe to me how to draw that, they'd say oxygen with 2 lone pairs, and then they'd say double bond, and I would draw 2 lines, and then oxygen with 2 lone pairs. All right? Let's do a couple more of those. Well, actually, I think we're just going to probably do 1 more of those. So we'll try that one. And then I'll talk about triple bonds, which are very much like the double bonds. And then you can work on the rest of those practice sheets. So again, draw your elements down, put the dots, and then you're starting to try to create some groupings of these lines. Because I'm teaching you about double bonds, there's going to be some double bonds in this. How many dots on the carbon? Oops. I heard 4. I want yellow. I'll right back on that. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And I'm going to draw the other one down here. 1, 2, 3, 4, 5, 6. Plans. What could we do? Yep. To the O. Okay, hold on 1 second. I'm going to do that for a moment. So 1 to there and 1 to there. I like it. Same to the top one. I like it. There, there. Which means then you've got to kind of imagine that they're wrapping around that way and connecting to it. So 2 double bonds. So I'm going to have the carbon, one of the O's on the back side. Again, it still has its lone pairs. And the other oxygen also double bond. And it also has its pairs. Okay? Nice job. Good picture. Does anybody know what that molecule is called? It's got a carbon and 2 oxygens. We're going to learn about this later on, but what do you think it's called? That's, no, you've got it backwards. It's CO2, but what's the name of that molecule? What's the name? Yep. Carbon dioxide. All right. What's that? Correct. Like in a little BB gun, those CO2 canisters, or in a paintball gun, or every time you exhale, in CO2 as well. Not that you're firing BBs or paintballs with your breath, but anyway. But the CO2 containers are compressed CO2. Yeah. Okay, let's try this one. And then I'm going to do the triple bond. I'm going to go to it as well. Let's try this one. Again, I'm going to line my C's up like this. Notice I have 4 H's. So how many do you think are going to go on each of the carbons? 2 and 2, right? So looking ahead like the other one, if I put 2 over here and 2 over here, I'm hoping you can start to see how they're connecting. We could do a triple bond, but then we still wouldn't take care of all the H's, right? So in this case, I need just a double bond. If I'm going to have an H over here and an H over here, and an H like that and an H like that, then I'm going to have my carbons do that. I'm going to swing everything around. And to draw it up, again, C, there's two of those lines, C, now we've got an H, 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 H. You don't have to have them up and out like that. That's the way I've drawn them. No, it doesn't matter if you've got them down or up or that type of thing. It's not a big deal. These molecules do have real shape. In the grade 12 university, I teach the students how to determine what that real shape is. This molecule is actually flat. It is flat. Most molecules are three-dimensional, but this one's flat, and the H's actually go out on an angle. So they spread out like a triangle. So they actually go out like that with a specialized angle in there. But you guys don't have to worry about that stuff. Let's keep going before I let you do that sheet, and we'll finish off with a couple of triple bond ones, and then you can work on all of the sheets. Okay? So let's do some triple bond examples here, and then you can finish off all the sheets. I'll let you work, and then I'll come around. Triple bond. How many dots on each nitrogen? 5. Because this lesson is about triple bonds, I'm thinking you can probably imagine I'm going to have 3 of these lines joining them. So I'm going to set it up so that the 2 are on the back and the 3 are facing each other. Remember, 1, 2, 3, 4, 5. Yep. Yep. That's beautiful. That's perfect. Exactly correct. Max had the idea of connecting 3 at one point. That works perfectly in this case, because there's no other atoms to accomplish that. We put 3 lines. We keep our lone ones. And just to make this note look like the rest, I'm going to give that guy a name. And what am I going to call this one? A triple bond. How many electrons are in that triple bond? 6. 6 electrons in there. We'll do one more example right there, C2H2. As you're writing down that last example, the question was asked, what about a quadruple bond? Could you have all 4 electrons in something like a carbon atom? Could you have all 4 of them bond together? All right, before I put the H's, you might think, hey, I could connect, I'm just going to use the mouse here as I'm talking about it. You might think, hey, can I connect 1, 2, 3, and then come all the way around the back for 4? In actual fact, you can't. This is a molecular model that represents a C with 4 H's on it. If I take the H's away, you could maybe imagine that it's going to try to bond with another carbon. All right? You can see how it's got a kind of a tripod shape. These 3 can bend over. They can bend, and they can form a bond. But this one is pointing completely the wrong way. If this tries to come over and make a bond, it breaks the other one, and it can't form that 4th bond. So as that tries to come over to another carbon and forms a bond, it breaks it, and it cannot form a 4th. So due to its actual shape, its 3-dimensional shape, a 4th bond is not possible. So to finish this one off, I've got 2 H's. Oops, that's not an H. That's a mess. I've got 2 H's. And you could probably imagine there and there. And then we can have our 1, 2, 3. And that's going to result in the C triple bond C with a single bond to the H and a single bond to the H. Okay, I'm going to stop my note at this point. On Google Classroom, there are 2 other sheets, one for double bonds and one for triple bonds. There's not as many on the double bond and triple bonds. You should be able to finish those off in about 10 minutes. And we can probably take them up at the very end of the class. We can somehow put them up there. It's dead? Okay. I'm going to just stop this video, and then I will come around and help.